Or welcome back. We're on chemistry, thermodynamics, worksheet for problem number 2. We just went through kind of the overall ideas that we've all seen in here already thus far. If this doesn't make sense to you, go back and watch the last video. We're actually doing number 2 now. So Sue plans to make pasta for dinner. Great. She adds 850 grams of water. Cool, that's a mass there. I immediately identify that. I notice the units are in grams, and all of my things here are in grams as well, so I don't need to change units there. Of water to a pot and places it on the burner, which is turned to high. Okay, cool. Just like you normally would. Sue checks the pot after 10 minutes and discovers it's boiling. Great. How much energy does the water have while it's boiling? Okay. Now this question right here is let's investigate it together. I'm going to go ahead and make like a little temperature blot here. Or here's my temperature, and here's time here, because we're like heating it over time. So I put it in, and as she heats it there, we know that it's going to be increasing in its temperature. So it'll look something like this, where this is the liquid phase. And then at some point, it kind of starts to plateau there. Not kind of, sort of, but it really does plateau. And that's the start of when it's going to a liquid to a gas. That's when it's boiling. And then maybe, hopefully she doesn't get to this point, but there'd be some point later where it's like, you know, just a gas and heating up. That I do that as a dotted line because it doesn't really exist there. And I have these vertical dotted lines here just to break up the little plateau versus non-plateau parts. Okay, so we're really just looking at the solid line here. And hopefully she doesn't boil off all the liquid, otherwise kind of hard to make pasta. So now we got to figure out how much energy is, how much energy does the water have? That's a slightly ambiguous question here, and we gotta dissect this a little bit because, well, to do that, we would have to know, hey, what temperature did this liquid start at? What temperature did it end at? Well, I bet we can actually. What temperature did it end at? 100 degrees Celsius. That one's easy. But what temperature did it start at? I don't know. It doesn't really tell us. So we're going to have to make an assumption there. We're going to assume that her place of residence is 20 degrees Celsius, or the water that came out of the tap was 20 degrees Celsius. Is it? Well, 20 degrees Celsius is usually considered room temperature, 20 or 25. Depending on the room itself. We don't have any of that information, so we kind of have to make a guess or an assumption somewhere here. I feel like that should be written into the problem there. Sorry, I didn't write this problem. So we're going to go ahead and make that assumption here, and then once it gets up to there, okay, so now there's like two parts here, you might say. There's like, hey, what's the change in energy going on in this part here? We usually call that Q. How much energy did I have to add to this in this case? And then, hey, how much energy am I changing as it goes to from the liquid to the gas there? And we don't know how much of this is actually getting boiled off. And I guess I'm going to kind of assume, because she checks the part after 10 minutes and discovers it's boiling. So she discovered it, well, we're assuming all of it didn't boil off. Well, she discovered it somewhere like there. And like how much, boiled off there, we have no idea. And it doesn't really tell us. So I guess I'm going to kind of like ignore this. But I'll show you how you would do that anyways, because she didn't really. Maybe I'll address that at the end, and we'll make up some numbers so you know how to do something like that. But in this case, you wouldn't be able to calculate that. So we'll kind of focus on this thing right here. And like I said, that beginning temperature really should have been written into the problem there. So now I look at that and I go, okay, cool. Well, I have a beginning temperature and an ending temperature, and as I'm going up there, I know I'm going to be using this equation here, the mass of that liquid there, times the specific heat, times my change in temperature there, and that will tell me how much heat I needed to add to that to change that temperature. So now we can go ahead and do that. We got 850 grams from the problem there, 850 grams. I multiply that by the specific heat, which is 4.18. Let's make sure that we didn't approximate that too much there. Yep, we didn't. And that is joules per gram degree Celsius. And maybe actually I'll write it like this because for most of the year we've been writing it like this. That's joules per gram degree Celsius. And I could add ones in front of there just like you can in math class. That doesn't change anything, and it's usually more descriptive too. I'll go ahead and change this to a fraction there as well. And now I'm going to go ahead and multiply by my change in temperature there. And my change in temperature, well, that's the ending one, like we were talking about. ending minus the beginning bit. And so notice that that comes out to be a positive 80, which makes sense because it's increasing its temperature by 80 degrees Celsius there. Okay, so that's that, and we didn't have to, I guess I'll go ahead and rewrite this, although I don't need to. Joules per 1 gram, 1 degree Celsius. And then 850 grams per nothing, really. It's just 850 grams. Now, let's go ahead and let's look at the units here. You don't have to look at the units every time, but I find it to be useful sometimes, especially when I'm like not sure if I'm doing this right. I look here and I go, hey, grams is in the numerator and grams is in the denominator. That's interesting. Look, if I made this a fraction right here, that's the same thing as 80 over 1. Degrees Celsius is right there, and degrees Celsius is right there. Now notice that the only unit that I'm left with is joules there, and notice I'm trying to figure out how much energy this thing has, and yeah, energy is measured in joules, like I said, after James Joule. And so that's what I ought to be looking for, and it is what I'm looking for. So now I just need to go grab my calculator. You're grabbing your calculator with me here. Good old sounds of the TI-83 Plus, my trusty dusty calculator. I'm actually using the same one I used in high school. Save yours, because it could be years later, and you could still be using that because they last forever. They're tanks. You probably already realized that because you've dropped it a few times. Anyways, I go and just multiply all that stuff like we know to do in math, and I get 284,240 joules, and that's energy. Okay, cool. So this is how much energy we had to transfer. Let me write that out. This is the amount of energy transferred to the H2O to increase its temperature. That's not apostrophe S. It's temperature from 20 degrees Celsius to 100 degrees Celsius. Okay, cool. Is that how much energy that H2O has? Well, I mean, that's a very, very deep question. That is a very, very complicated thing because there's a lot of energy like in those bonds themselves, and we could take that in many, many different directions. So even that initial question there is a little bit ambiguous and a little bit overarching there. But we definitely can calculate the transfer of energy that we needed to transfer to that to increase its temperature. And that's what the question, I think, was originally trying to get at. Now, what about this little bit here of like, hey, she checked it after 10 minutes, found out that it's boiling, and so that means some of this mass here got boiled off. Now, I think this is probably beyond this question here, but I'm going to go through this anyways, because you might come across some other problem where you might need to understand how to do something like that. So let's go ahead and kind of write our own problem here. So let's say that 15 grams, let me write it like this, 15 grams of H2O boiled off before she checked it, before she turned off the heat, So then the question would be like, how much energy did she need to transfer to boil off that 15 grams? So energy needed to boil off 15 grams of H2O. So that's the real question. And so how would we do that? We would go, oh, well, I'm not increasing the temperature of that H2O as it's going through this, as I'm boiling it off. And when we say boiling off, we're going from the liquid to the gas. And so whenever you see that steam coming off the pot there, that's literally the H2O that was in the liquid form, and now you see it going into the gaseous form. Now, actually, technically, that steam that you see rising off, you can actually see H2O in the gas form. As you know, whenever it's like humid out, it doesn't look any different. It just looks like air. You can't actually see H2O that's in the gas form. However, what you can see is H2O when it's in the gas form, it might actually cool down enough where it goes back into the liquid, and then it looks like some sort of fog, or in this case, steam. And so what you're actually seeing when you see the steam go off there, it's actually water that's gone from the liquid to the gas form, because we're like boiling it in that case, but then it hits that cooler air right above it, and it might cool down enough where it actually goes back into the liquid form, and that's why you can actually see the steam there. And that's, you actually do that in your mouth during the wintertime. Because when you breathe in the wintertime, you see that breath come out. Well, your breath is coming out with all that moisture in the summertime. Why can't you see it then? Well, it's only because when it hits that cold air in the wintertime, that cold air cools down the water vapor enough that it actually is transferring it from the from the gas form to the liquid form, and then you can actually see it as the condensed water vapor in the air. You see that as the cloud of air coming out of your mouth in the wintertime, or out of the exhaust of a car that you're driving behind. So we see that all the time. Can't actually see H2O in the gas form. Okay, but you don't need to know all that, but interesting. I think so. Anyways, so how much energy does it take to transfer 15 grams of liquid H2O to 15 grams of gaseous H2O? We could actually write that as an equation here. We're going to do like 15 grams of liquid H2O, and we're transforming that into 15 grams of gaseous H2O. So then when we go and do that, we go, oh, well, I'm not changing the temperature of that thing, but I am changing the state of that thing. And here's where that second equation comes into play, where we're using the change in enthalpy, or the heat of boiling, as it says here. And it's just how much energy it takes to go from a liquid to a gas, specifically of H2O. And so it's just 2,260 joules for every gram. So I'm going to start with my equation here. Q is equal to, it's actually delta H there. I'll write it as delta H. It doesn't matter. Times the mass. And then, so then I'm going 2,260 joules for every 1 gram. And again, this is of H2O only. Multiplied by the mass there, we had 15 grams of that thing, and divided by 1. And we see that, hey, if we look at the units there, like we did before, that's useful. I see that the grams cancel out there, and, well, that makes sense, because I'm calculating the amount of energy there. The amount of energy is in just joules, which is the only unit that I'm left with. And so basically, so all I'm doing is 2,260 joules times my 15 grams there, and I get 33,900 joules of energy. Now, again, at the beginning of this question here, I don't think they were actually going to look at this bit, but hey, there you go. You got a little bit extra, and maybe that'll help you out for some of the other ones, or in worksheet 5. Or anyways, so that's it. Oh, it also has circle endothermic and exothermic. Well, as it's heating up there, it is gaining in energy. Well, let's do this last. Let me do that in teal. As it's heating up here, the H2O is gaining energy there, and so gaining means heat is coming into that like endoskeleton. If you remember from biology, endoskeleton, we have endoskeletons. They're skeletons on the inside. Endo means in, and so that would be like an endothermic thing. Exo means out, like an exoskeleton. Ants have an exoskeleton. It's like hard if you accidentally like crush them or something like that. Because the entire exterior of their body is not soft like our skin, but instead is like a hard shell, because that is their skeleton. And so exo means out. And so if heat is going out of the thing, then it's exothermic. Cool. That's it. I hope you have a wonderful day. See you later.